Spasibo, Poopsie. We are on Chapter 10, Generic Types, Traits, and Lifetimes. We've learned about a couple of these before. I'm excited to learn about lifetimes. And it seems like we are, after today, halfway through this book. We have one important chapter, obviously writing tests. But more than that, we have a project coming up. And I am itching to start using Rust as a regular tool in my tool belt. It seems like every time I try to write something with it, and this is on the side, not something that I'm actually doing with you guys, it feels like, okay, I'm pulling teeth. I'll learn about this in a little bit. I actually had a comment that was like, hey, you mentioned asserts in your last chapter. They exist, and here's how they work. And it's like, thank you. I appreciate that. But I'm also trying not to read ahead in this, to give you guys the best example of somebody who's just working through the text and saying, this doesn't seem to make sense, or this was great and I really like this. Enough of me rambling. Let's get into Chapter 10. Great. I am done with Chapter 11. It seemed like this was a girthier chapter than the ones preceding it, and judging by what we have accomplished so far versus what we have yet to accomplish, we're close. But it looks like there's a little bit more in these later chapters, more meat on the bones. Let's get started by talking about generics in the same way the book does. They had a brief aside about how we might try to find a generic in code that we're writing, like when's a good time to use it, but looking at data or functions, not functions, but code that does the same thing that you could break out into a function. And in the case where you have different types going into that function, instead of having an enum and then having it match on each of those different types, which we've seen in the past, we can use generics. It's almost like the name is very apt. So we've seen these before. We've seen the T before, which is for the type. We'll see in the greater than, less than braces. And we see basically you can pick whatever you want after that. It used you. It didn't say why. Anyway, syntax aside, it actually talks about our enums we've seen before, our result and our option. Very similar to what I talked about last time. The type definition gives us information as to what it's going to contain and how it's going to be used, which leads me to my first introspective thought of this. The result here has a type of T and E, and strangely, we have E, and it doesn't have any typing information because it's a generic. And I feel like we could have used some sort of trait to specify this needs to be inheriting some sort of base error class. We talked about that last chapter and saw it was standard error. Well, I could be wrong about that. But it seems like if there was a way to say this generic type needs to implement this kind of behavior, foreshadowing, traits and all that, then we would want to have some typing information here. And it doesn't look like the source code actually does that. I'll leave it to future me to decide if that's worth showing on screen right now. If you're looking at it, then you know. It feels like this might be a good case where we could specify like result needs to return an error. I'm now wondering if I can wrap E in anything other than an error, or if this logic doesn't exist in the declaration of our enum result and instead exists in the what error accepts as what it can wrap. Immediately after this, in listing 10.9, we have an example of something that makes me personally kind of upset, which is a getter that does nothing. There's a little bit more to dig into here because this is a method, so we're talking about a reference to ourself, and we also have interesting new syntax where a generic, something that operates on a generic, needs to have the implements and then the brackets for whatever type of our actual struct. So that's interesting. I'm not a huge fan of how this looks, and after reading through the rest of this chapter, there's more to talk about in terms of referencing something here and how this actually works, because yeah, we have a reference to something that's being returned that's also part of the parameter space, and the compiler can optimize that out, but hint, lifetimes. It then immediately points out that this T inside of our implements point doesn't need to be T. It could be whatever we want it to be. It just makes sense to continue to name it based off of the struct's generic name. We could put Y, or are you doing this, or don't make getters that do nothing, off of my soapbox. But yeah, we also immediately see we can actually change this type so we don't have a bracket, so it's no longer a generic, and then force a particular function based on the type of the inside attributes of this point struct. So in this case, we have f32, and we have some more wonderful math functions. We have pow_i, which is an integer power, and presumably we have pow_f. But what's exciting about this is pow_i will return a float, right? Because we're dealing with floats. So we know that pow_i is something that we should expect to see in f32. And moreover, we see square root that should also operate on floats. Presumably f32, I'm going to assert f32 based on the typing of this, but let's see if it exists for f64. I don't know why I'm saying f. It's floats. We get a more complicated example in listing 1011, which is frankly very confusing to look at on first glance. We have x1 and y1, which are generics that can be two different types inside of our point, and then we have a function based a method mix up, which kind of takes two different points. We have one would be like self, and then this other one we're passing in as a parameter, and so we need to specify a way to talk about the different types of both of those. Well, in mix-up we now have x2 and y2. So our method needs to specify x1 and y1, the types that exist for our struct, and then mix-up needs to specify two different types, and then we need to return a mixture of both of those because of the mix-up function. So the return is going to be x1 and y2. I feel like this works fine. There's no problem here. I wonder if there's a way you could say, I need to specify the typing information for this, but I don't care about it in the way that you use like an underscore for variables you don't intend to use. But I recognize maybe this is a good example as to why that can't be done, because if you used an underscore, it might assume that all of the underscores types in your generic are of the same type. That's really hard to write. I might just write this code out and see what happens and if it explodes. But the only thing we need to know is that if we have multiple different types, we can specify that in the declaration of our function and structs, and then use, you know, a bunch of different generics here. There was one thing that I need to confirm with some smart people, that's you, where we're using p3x and p3y. And so, well, what is p3? P3 is the output of our mix-up, which is in itself a point. And so the point has these attributes, x and y, and would you look at that, they are not public, right? Nothing here is public. So we're looking at this implement here, and we're able to return p3x and p3y. This doesn't make sense to me because we're no longer inside of our implement definition or our struct definition. I would assume that we could say x and y here, right, inside of this implements just fine. But now that we're in main, we shouldn't be able to access x and y. That feels like a reasonable statement. So I'm wondering how this is actually accessible outside of our struct and our implement definition. Let me know if I just repeat myself too much. I feel like a total pedant. And would you look, the book does a much better job of explaining all the rambling I just said. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with implement and some are declared with the method definition. Ta-da! We then get, in my opinion, a very cool aside, which is how do all these generics affect performance? Essentially, it's saying that the compiler is smart enough to know that when you're using a generic, we know the types that you're trying to use inside the generic at compile time, and then can create any number of those particular offshoot branches and include those in our actual binary. So we're not having to do any sort of runtime special checks. It's actually all done at compile time. So the performance at runtime is going to be perfectly fine. It's negligible, well, not negligible. It's going to be the exact same. I wonder if you have something particularly heinous, I can't imagine you'd use something that large, whether or not the compile time is going to be much larger because of this kind of optimization at compile time. Definitely makes sense. Don't do it any other way. Not a complaint. I'm just for my own edification. And that's all we really needed to learn about generics from here, right? Like, how do we use multiple generics? What's kind of actually happening under the hood? Here's how to use them. You can use them differently in methods than in the struct definitions. But now we're on to traits. New exciting topic. This has been a bane in my understanding of how Rust works. Let's see if it made any difference. Surprise, I already read this. It did. I like the way that the traits work for this, though I do have some broader programming questions where things kind of correlate, and I'm not sure if there are ancillaries between Rust and them. But traits, I'm thankful. It starts off by saying traits are like interfaces in other languages. You are specifying that a particular type, a particular struct set of data has to conform to some set of behaviors in order to make everything happy. And this allows the compiler to be smarter and to make less assumptions, which is the whole point of typing something out and making sure that the compiler can save you from these problems. They don't become runtime bugs. As a small tangent for me to complain, there is a concept in other languages. You call it duck typing, which is essentially, I don't statically define a type. It just take whatever you put as a parameter, whatever. As long as it walks like a duck and quacks like a duck, it's a duck. Right? I don't care what the actual type is. As long as it has the attributes I'm expecting, as long as it implements the same functions I'm expecting and can operate on those, then I don't care what the type is. That's cool from I'm lazy and I just need to make something work. And you'll see it whenever you try to execute something on that duck if it doesn't work, but you see that at runtime. And so traits are a way that we define explicitly to the compiler, this is what I'm expecting this thing inside of here to do. This parameter must be able to meet these behavioral requirements. And I think that's nice. It makes a lot of sense. I'm a little bit taken aback because this normally is done through creating like a parent class, and then you make like essentially an abstract of here are all the things I expect it to do. And then when you create that, you have to make those functions. And that's leaning into the object-oriented side of things a little more than I'm comfortable with. So it makes sense that this is its own beast because we're not really using a lot of those object principles here. We're really just trying to ensure that the compiler knows the behaviors we expect. And yet again, I highlighted a sentence that says all of the things I said. Brevity is the soul of wit. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. We then have the first example in the book where we are making a library crate, and we're not just talking about our main binary crate, at least outside of the modules chapter. And then we'll get really confused in a couple examples when it says use aggregator, and then you're like, is that part of standard? You didn't specify where is that coming from, even though it says aggregator here and then a couple other times. Anyway, so we're actually making a trait here, right? Our first example of using a trait, listing 1012. So we have a summary trait, and we specify that anything that implements summary must have a function called summarize. So this feels very similar to implement, but the trait is more abstract. We don't really know at the time we're creating it all of the intricacies of all the things that are going to be implementing this, obviously. That example's fine in itself. One thing that I'm not sure of, it says we declare the trait as public so that the crates depending on this crate can make use of this trait too. There's probably a good example somewhere where you have a remarkably large and sprawling library, and some things inside of that library all need to have some behavior, but that behavior does not need to be known to the person who ends up importing and using your library, where you wouldn't need to make your traits public. That feels like a very weird edge case that I personally don't know if I've ever really seen. So I'm assuming almost all the traits we're going to be writing are public because we're making sure that people know the inputs to a thing that we create need to have this behavior. I didn't mention this as well, but we actually don't use the curly braces to define what summarize does, right? This is abstractly, we're saying this needs to use summarize. It is up to whatever is going to implement summary to create what summarize does. We're saying it must be this. Flash forward I mean, I hope that you read the chapters before me and it's like a similar experience where you're like, wow, okay, he noticed this and I noticed this and that's great. And now there's friendship and community and camaraderie. But if you're just going along with me in this project, you already know that we are going to be implementing traits where we specify the default behavior of some trait function definition. Is it a method? It feels like a method. Well, I'm going to say method definition. In this case, we're using self. It's a method definition. And hey, we have an immediate example listing 1013 where we create two different structs, a tweet and a news article, and both of them are going to implement our new summary trait. So we say implement the trait name summary for whatever our struct is. So news article. And then because we've created this and that this summarizes abstract, we then need to, for each of our structs, specify the behavior for our summarize function. And an obvious thing that's worth pointing out, I guess, is our summarize function definition for news article as well as tweet needs to be exactly the same parameters and return types. That's kind of the point of what we're expressing in a trait. And if you're like me and have some questions like, well, how does this actually work? We have an example. So we're back in a binary crate. We know that because we're using our aggregator crate at the very beginning of this. We have to implement our trait as well. So even though we're not actually calling anything on that trait, right? We're not instantiating anything directly from the trait. We're saying we want to instantiate a tweet, but a tweet implements a summary. So we have to make sure that we we have to bring into scope our summary. The rest of this seems pretty obvious. It's the same stuff we've seen before where we create a struct with some data, initialize a struct with some data, and then we can call our method on tweet. And this method needs to be checked to ensure that it is of the exact same definitions we expected for summary. The book says as much. The only difference is that the user must bring the trait into scope as well as the types. We then get some useful guardrails before we get to our default implementations. I'm just going to read this out and hopefully be able to talk through the examples in my head. We can implement a trait on a type only if the trait or the type or both are local to our crate. For example, we can implement the standard library trait like display on a custom type like tweet as part of our aggregator crate functionality. Because the type tweet is local to our aggregator crate, we cannot implement external traits on external types. So if I'm understanding that correctly, I can't say, hey, I need to implement display or something in the standard library to some library crate that I imported because I didn't create either of those types. And I'm trying to enforce behavior to something that I didn't actually create. So as long as it's local, as long as we're creating the type, we have a lot of flexibility to say this behavior over here needs to apply, or I wrote this behavior and I'm writing this type. Let's slap them together. It says this is a orphan rule because the parent type's not present. Very cute. Now we get to talk about our default implementations. So we created before a summary trait and a summarize method, but again, it's kind of abstract. It doesn't do anything. If we said, well, I don't want everything that implements our summary to have to define its own summary, can I just say inside of my trait, this is what I want summarize to do? Yes. Now that behavior can actually get a little bit confusing because if I create a type that implements some particular trait and I want to make sure that whatever the behavior I overwrote inside of a method in my type overwrites what's been written as a default inside of the trait, how do I make sure that that happens? I mean by that specifically, there's ways that we have to tell the compiler, this is the behavior I expect. And I've seen that through things like virtual functions where you expect the compiler to do some extra work to ensure that whatever you wrote in your subclass is the main thing, even if you're calling it from the parent, but we're not actually instantiating anything inside of our parent trait. It's just kind of a blueprint. There's no creating of that parent. It's not objects yet. So it still makes a lot of sense. I'm not sure if that's super hand wavy. I'd love to talk more about why I think those are kind of weird, but not from a performance perspective, but from a writing code perspective. That's neither here nor there. It basically just goes on to say your default is your default. So if you make a trait and then you make a type below it that implements that trait and you don't overwrite the behavior of any of those defaults and you call that method on that type, it's going to get the default behavior. If you do override it, you're going to get your overwritten information that's just available to you. I have a sticky note here, and I'll explain roughly what I'm thinking. If I have a trait and I'm only concerned with defining behavior, I might have something that is predicated upon some attribute of that trait. I might have some behavior instead of some data that needs to be standardized. So we have this idea of an author for something we need to summarize. And that's different between our tweet and our news article. In our news article, we have an actual author attribute. And in our tweet, we have a username, which acts as this author. It seems like it might be easier, and maybe this is leaning too much into the things that I know and the behaviors that have been bad in their own ways for me. I wonder if there's a way inside of our trait that we could just specify this attribute should exist in anything that implements this trait. And this attribute's name is called author. So that way inside of a default, we could specify just whatever self is .author. Instead, we kind of get a weird roundabout way of doing it, which is I then have to make an abstract called summarize author, and then anything that implements it has to come up with its own definition of what summarize author ought to do. And because the attributes can be different, i.e. username or author, then we have two different implementations, two different functions. It makes sense that if I say you're making a type, it needs to implement summarize. Summarize must have an author attribute. And then in that, you could say, when I initialize it, well, the username for tweet is actually the same value as author, right? It seems like you skip a step there rather than having to make more functions, which is fine. I like the idea of just saying, what is the data and how am I referencing that data? And it seems like that makes more sense. It might be too much object oriented. These are classes and objects than just structs, but maybe that makes sense. I don't know. I'm rambling. Afterwards, we have the next question of how do we use these traits outside of our definitions for types? Well, we can create a function, and the parameter we say has to implement some particular trait. And that means inside of our function, we can demand some behavior exists, even though this item, right, may be different types. It's very similar to the way we were defining generics, except we're defining the behavior rather than specifically the type. That's pretty cool, right? It's the same behavior as generics, but a lot more concrete in what we expect the generic to do. So I say item, I don't care what type it is, must be able to do all the things that the summary trait says it should be able to do. And then inside of here, we can do things like item summarize. The book then goes on to say that very explicitly, right? Item is a generic type, and that generic type must be able to do all the things summary says it should be able to do. But we get this nice syntax that says all of this right here, and that's nice. I'm going to try to continue to say trait bound if I'm being verbose in saying, yes, item is in fact a generic, but I'm probably going to forget that, so forgive me. Before I read this next step, I was thinking at the time, I wonder if there's a way to, when we define our trait, to specify it needs to be able to implement something else. Again, this is hierarchical thinking and maybe not the best, but if I wanted to say like report or something like that, it may make sense for me to say, well, this report self needs to be able to use display. And it might behoove me to say, actually, everything that needs to be able to implement summary must be able to also have display. We can say that for any particular function, this is where I flip ahead into the chapter, we can say that for any particular function, whatever our generic item is, must be able to do summary and display. But I'm wondering if we can just nix this display and ensure that anything that's able to implement summary must also be able to do display outside of any particular function. This is definitely more, what is a good word for that? Granular? This is a lot more like specific to small pieces, right? But if I wanted that overarching behavior on everything that needs to implement summary, I wonder if that's possible. The book then goes on to quell the nerves of people like me who get concerned about how this would work in a very big and complicated system. And yes, if we have multiple types and we're using our trait bounds and we need to enforce very specific rules, It could get particularly unruly. It gave an example where we only have 2 different generic types we're importing, and they have different expectations in terms of traits they have to implement, and it's kind of hard to parse. And if you had 5 parameters, oh my goodness. So yes, we can break those out, specify all of our types inside of the single line function definition declaration, and inside of a where we can specify all the traits that each of those particular types need to implement. What a sentence. And obviously we've talked a lot about the parameters and how they tie into traits, but what if we have a return type that needs to have a particular behavioral constraint? Well, we can implement a trait to a return type in a function definition, meaning that whatever we return, could be whatever, must actually have the behavior of summary. And that makes sense. Foreshadowing, return types are a great way to talk about lifetimes, but we're not there yet. Why would somebody need to return a particular trait in a return type? Well, we have the collection things like our iterators, where we're returning one particular thing in a list, and the way we iterate through that list is important, and the behavior associated with that's important, but we don't know the actual data of whatever we're iterating over. It says as much immediately below. And it also talks about closures, so functional programming, which is foreshadowing chapter 13, but not there yet. The return type implementation syntax is useful to cover now, but we're not actually able to use this to its full extent in terms of defining a library which enforces some behavior on the return type, because we don't have the ability to express concretely to the compiler what types can exist there, like returning that generic of any number of things, or let's say something outside of the parameter space, isn't obvious to us and also not obvious to the compiler. And so our example where we have a news article and a tweet type, they both implement summary. So a definition like return summarizable with a return type of something that implements summary seems like it should work. It turns out that it can't. It says as much, and then goes on to say, we'll cover how to write this on like page 400. We're not there yet, but as a quick patchy kind of way to get this done, if we're not talking about a library, if we're talking about something very concrete, for example, our return summarizable, we could always make a new enum type which can wrap our news article and tweet types and then enforce that as the explicit type here. That's not useful in the case where you don't know explicitly what you need to return, but hey, we work with what we got until we get to page 400. I mean, hey, we're actually halfway there. The book then goes on to say, here's how you can create a method for some particular type that needs to enforce some traits. Same implementation bucket we've been talking about. We have implement for a pair, but whatever this T is that we're putting inside of pair must be able to use display and partial ordering. I'm assuming that's ordering because it's doing the greater than symbol. Anyway, if we don't have both of these, we can't use print line on whatever X or Y is. And moreover, we also need to have this ordering because we can't do this if check, this greater than or equals to between X and Y, if both of X and Y don't implement the trait of partial ordering. This all makes sense to me. The reason I think the book points this out, one is it explains, hey, this particular method will work on a generic type where we expect some behavior, but we also talked back about the performance hit potentially of generics, where the compiler will kind of build out all of the different things that we're going to be shoving inside of this generic at compile time. Well, it doesn't make sense if we have pair here with something that doesn't implement display and partial ordering for us to have this compare display function created for it. So the compiler can prune down all the things where it needs to create compare display for whatever T actually is when we create it. Man, what a sentence. I feel like I'm saying all the things I am intending to say, but I also feel like there's like so many words there. It's very hard for me to follow. I hope that made sense to you. The book then moves from our conditional methods, where we're saying implement this method on the condition we have these traits satisfied for our inputs, to a blanket, which is the opposite. We want to make sure that some behavior exists for everything that has a trait, but we don't necessarily know what those traits are. And it says this happens a lot in the standard library, but as an example, we have implement toString for everything that has display, and then toString does some stuff. That means that if we create a type that actually implements display, then we can call toString on it. As a blanket, we just get that because all the things that toString must do only have the requirement that display exists. The book gives us the example. We can turn integers into their corresponding string values because integers implement display. Because whoever wrote integers made sure that it implements display and follows whatever behavioral trait definitions display requires, we just get toString by default. So if you're like me, your head's probably spinning with all the different ways that traits and these generic type bounds all work together and the consequences of that. But we're going to move on to lifetimes because it also relates to the way we declare our functions and how the borrow checker might get confused when we reference something. One small note, I believe it actually talks about this here, but in case it wasn't obvious to you, a reference is just a pointer. When we're returning something like a string slice, we're returning a pointer to some data. And that can be problematic, as we saw in the last chapter, and I believe a couple chapters ago. We want to return something that's implicitly a reference of some parameter that goes into that function. The compiler may not be able to know exactly which one of the parameters, if they exist, how long whatever our inputs are must live in order for the return to be valid. I think I've said as much as that before, and I'm not sure if my editing will make my hand waving any less confusing, but hey, it says we must annotate types only when multiple types are possible. In a similar way, we must annotate lifetimes when lifetime references could be related in a few different ways. So the relationship between whatever's going into our function and a reference in the output is not obvious, and making a lot of assumptions there can be bad. So lifetimes are a way to say, hey, this output is related to maybe this one parameter here. So as long as this is alive, this should be valid. Subsequently, if either of these could be alive, well, when you're thinking about the output here, consider both of these guys. Whichever one lives the shortest, that's what you should be concerned about for the lifetime of my return type. I said return type, I meant reference. It's pointers, okay? I've rambled a lot about this. I'm not sure if it even makes sense. I think that the way the book describes it's fine. It didn't really sink in the first couple of times I read it. I think it makes more sense when you make explicit the correlation between something referencing an input and how long the inputs are alive. I think that makes more sense to me, like plainly stated, but hey, we have syntax to talk about. So in our signatures, which we're already getting kind of unruly, we need to specify the relationship between an output reference to some input parameters. We do that inside of our square braces, putting a single quote and then a short lowercase thing. They use a, makes sense. So in our example of something like longest, great example, we have X, Y, and our output. In the example in 1020, we have a reference string, a string slice, to either X or Y. So the compiler cannot know beforehand what specifically we're going to be returning in our output. It could be X, it could be Y. We now have confusion about what lifetime's related. We can explicitly solve this by saying, yes, both X and Y are related to the output. Make sure to check that wherever I would want to be using the output of longest, that we are using a reference to X being alive or Y being alive. If they're going to die, then we have a borrow issue here. We have a dangling reference. So we say, hey, there's a lifetime we're concerned with. It's A, and A is going to relate to X and Y and our output. Or more briefly, all the references inside the signature must have the same lifetime. When I first read this, I was a bit confused because I was like, we have definitely returned a string slice, which is a reference before, and we didn't have to specify lifetimes. And yeah, the book goes on to talk about that, but hey, we have more of the consequences to consider when we're thinking about lifetimes to talk through. There's a lot of text that talks through this, and I've already explained it. You probably have read it. You're probably like tired of hearing me talk about it. I think by this point it was pretty clear what this means, but I like one particular thing at the top of 206. It says, remember, we specify the lifetime parameters in the function signature. We're not changing the lifetimes of any values passed or returned. It's just explicitly telling the compiler, consider this particular lifetime of a parameter in relation to the output. You're not saying this input is going to change its lifetime. You're just saying the output is only valid so long as these inputs are there. I've said it again. I keep repeating myself. I only highlighted this. We're not changing the lifetimes of any of the inputs because it makes it very clear what we need to do when we see a particular error. So when we see something like this does not live long enough, it's not saying that we can fix that by changing anything inside of a function signature. It's saying that our inputs, we need to consider the scope and the lifetime of those. So lifetimes are funny. It's only pinning a reference to an input. It's not really dealing with like the lifetime of the thing. So really, when we see something like live long enough, we should say, okay, parameters and scoping, that's where the problem exists. I say that, and immediately after the book says, okay, that's true, but also you have the more obvious answer of just taking whatever the data is you're referencing and just returning a copy or a clone of that. The best fix could be to return an owned data type rather than a reference. So calling the function is then responsible for cleaning up the value. So obviously, as engineers, the answer is it depends. And this is one of those cases where it might actually make sense, instead of saying, hey, I need to return a reference to something, it might just make sense to clone it inside of the function. And then, hey, whatever I'm returning, now you're in charge of it. You've created it with a let, you're in charge of it, you're the owner. More lifetimes, more lifetimes. So we have an example here where we create a struct, and the data inside of that struct, one of these attributes, is going to be a reference, right? We're not just copying the data outright. We've seen this in the past where instead of using a string slice, we make a capital string string. And in this case, we say, no, we actually want to use a string slice. So this struct needs to be concerned with how long whatever its data is referencing. We do that by specifying our little angle brackets, quote A, and then whatever our attributes are inside of the struct, we can provide the quote A before the reference. I'm just going to point out my own personal W's here. We have a ampersand quote A. We know that wherever we're using a lifetime, it has to be related to a reference, because if it's just its own data, there's no lifetime to concern with. We own it. But I wrote at the very beginning on 205, when it starts talking about lifetimes, I'm like, more like ampersand quote A syntax, because yes, if ever you're using single quote whatever, whenever you're specifying a lifetime, it comes immediately after a reference. So that helps us in understanding syntactically where this needs to exist. We place lifetime parameter annotations after the ampersand of a reference, using the space to separate the annotation from the reference's type. So when we're talking about lifetimes, we separate the ampersand from the type and we put our lifetime right next to it, because of course it's more related to the reference. The book then does my favorite thing, which is validate my neurotic thoughts, and tells me, you are correct. We did return string slices before, and goes on to talk about elisions. I looked up what the word means. It means emitting something. So we specifically have the ability to return string slices. We've done it before, but we didn't specify lifetimes. How does that work? Thank you for asking. There are currently 3 rules that we can consider in terms of how the compiler considers what lifetimes need to be explicitly called out, and which ones we've seen so often that it just is a pattern and the compiler should be able to handle it. It calls this out explicitly by saying, hey, in the future, maybe there's few lifetime annotations you have to concretely specify, but for now we have 3 rules. It's important to note that these 3 rules will only apply if we are returning a reference. Otherwise, it's not necessary for the compiler to do any of this thinking. But the first rule is that we are going to create a lifetime that is unique to each one of the inputs. So all of the parameters get their own lifetime, quote A, quote B, quote C. That makes sense. Second rule is that if we have only one input, then we're going to take the lifetime of our input, quote A, and then put it on the output. And lastly, if we're talking about methods and we have self, we would take the lifetime associated with self and ensure that that exists on all of the outputs. That makes sense to me, but let's go over some examples so it sticks in our brain. Listing 1025, we have returned a string slice before and it just worked. How did it work? Well, we have a string slice. We're returning a reference. Let's go through our 3 rules. Firstly, we're going to apply a lifetime to all of our inputs. We only have 1. So S gets a lifetime of quote A. Now we're done with the first rule. Second rule, if we only have 1 parameter, we do, then we're going to apply the lifetime of that parameter to the outputs. Lifetime quote A then gets put on our string slice. Third rule, are we talking about a method? We're not. We're done. Let's make sure that this makes sense. So our input string is a reference and our output is a string slice, a reference. Our output must be related to our input's lifetime. This does not explicitly mean that we're not going to have any sort of borrow checker issues inside of our function. If we, for example, created some random string that was string from blah, 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 and then our output, or we say return a reference to some random string, when the scope of our function, first word, is done, we still have the problem that it's going to be cleaned up, and so that reference is dead, and we're mad. But in the case where we are returning something related to our inputs, we already have the behavior of the lifetimes specified by the compiler. In this case, first word, we're going to iterate through some stuff, and we're going to return some stuff. We iterate through all the bytes, and then we say find the first space, and we return everything up to that index. Then that output is related to our input, and we are happy. We don't have to specify that. Let's look at our longest definition back from 1020. If we have x and y, first rule, we apply a lifetime to both x and y. X we'll call quote A, y we'll call quote B. Now rule 2, do we have one input? Nope. Okay, rule 3, are we talking about a method? Nope. Our output reference is not clear. Is it related to x? Is it related to y? We don't know. We as humans can look at this and say, we don't know whether or not x is longer than y when we write this function. So yeah, we need to concern ourselves with both x and y. We have one lifetime. It's related to both the inputs. The compiler doesn't know that. So the compiler is like, I don't have any sort of elision rules that make sense of this. I'm going to throw a warning. You have to fix it. Shitty, why haven't you given an example of a method that needs a lifetime and concerns itself with these elision rules? Well, we don't actually know what something that implements a struct that has a reference as one of its attributes, what a sentence, looks like. So the book gives us an example. We can implement something that has a lifetime by specifying square brackets and then saying quote A. So we're talking about a lifetime A related to important excerpts, lifetime A. So when we create that struct, we look at the type, we look at the lifetime, and we say, great, implement must also concern itself with that lifetime. Then any method must also be concerned with that. Does this make sense? So announce and return, we have a function here, print line, announcement. So we know that announcement must also have the display trait, but it's a string, so the compiler can probably infer that. Then we have one return type. The return type is of self, self.part. Great, self.part is related to self, so our lifetime chain is now complete, and we don't have to specify the lifetime. Did me fake enthusiastically going through the rules solidify this to you? It did for me. I feel like one thing's worth pointing out here, that these rules exist only because they follow a pattern that is super ubiquitous. For example, the case where we positively used our third elision rule, we have a return of self, which tells us that most of the time that we're talking about a method, we're going to be returning something related to self. So it's important for us to concern ourselves with the lifetime of the method. It obviously makes sense when we make a distinction between methods and functions. Similarly, if we're talking about our first rule, if we have one input and one output, and that output is a reference, it's probably worthwhile considering the first input is going to be related to the output. Otherwise, the compiler will probably find that warning because it's a scoping issue related to the length of the function. Great, so we are intimately aware of the 3 things the compiler is doing by default to make the usage of lifetimes easier. Are there other edge cases? Yes, we have a special denotation called static, which is related to things that live the entire duration of the program. It says so much, and it makes sense because when we're talking about a compiled binary, we have a data section, and text is going to be something that exists inside of there. It's not something that's related to the scoping of it. It's always accessible. Why are you telling me about this book? Thanks for asking, Shitty. The reason is because we can sometimes see errors related to this static lifetime, and in that case, it might actually have some hinting information saying you should use a static lifetime. Since this is something that's going to exist in the data of our function and is largely handled by the compiler, when we see this error, it probably means that we're doing something fundamentally weird with a reference, and it makes more sense to actually fix that weird thing rather than to try to just make it static. I love this. I think it's great. It's somebody who's writing educational material being like, hey, this error will only make sense if you have this understanding. By the way, this error implies the following: fix whatever lifetime conceptual thing you're trying to do here. You're probably doing it wrong. Goodness gracious, there's so much stuff we've talked about. Are we done yet? Yes. No, we're not. We have one more thing to talk about. Our lifetimes are going to be using this greater than, less than syntax surrounding implement and the types and all that. But we also have another example where we're going to be using the the greater than, less than syntax. Generics, we talked about them this chapter. Let's merge these two ideas in a cute little cohesive thing, and then we'll be happy. We have an example here. Let's see if it makes sense. So we have longest with announcement. It is concerned with two things. One, a lifetime. Two, a type, a generic, T. Let's look at our parameters. We have X, Y, and an, which an is going to be a T generic. X and Y are string slices, i.e. references, and so we might concern ourselves with the lifetime, our lifetime A. Now we have an output. Our output is a reference. We're definitely talking about a lifetime. So now we have a string slice that needs to be related to X or Y, and that's because X or Y could be return types, and the reference, that is our output, is concerned with the lifetimes of X and Y. So if we need to specify this particular case, we now have all the tools. We just need to know the syntax. Inside of this, we say longest with announcement, and in our brackets, instead of just specifying the generic or just specifying the lifetime comes first, comma, space, our generic types. And I think we're officially done. I think that's everything in this chapter that was interesting. I'm definitely going to have to spend a lot of time in the terminal to make sure that this all sinks in. And I think the book understood that my mental stack was filled to the brim, about to overflow. And it says, yeah, don't worry, there's more stuff to learn. For now, we have a really good baseline of saying, yes, we understand how to use multiple generics, and to ensure that we can specify traits on those generics, what traits are, how they actually function in terms of creating something that needs to specify concretely some behavior, as well as if we need to implement something that requires a trait. What does that syntactically look like? What are the concerns there? And then finally, here are all of these lifetimes and how lifetimes are associated with references. So more familiarity with pointers, dangling references, all that stuff, how that all ties together in what would have been a remarkably complex and confusing signature, which we just went over. I need a nap, I need a refill of my coffee, and then I need to see if any of that stuck in my brain. Hello, handsless me here. On the left, we have my main binary, and on the right are the things that I'm going to call. Unfortunately, not a lot of what I'm talking about is related to the topics in the book. Mostly it was just me writing it and then executing it and saying, okay, that makes sense with what was given. I have some small things, and given the fact that as I edited the book part, I recognized we were closing in on an hour, I want to make sure I am nice about the time that you have. Largely, this part is just more becoming muscle memory. Fingers crossed it stays that way. One thing that I thought was interesting is as I was writing this, I wanted to see what sort of warnings I would get and what sort of errors I would get if I didn't know the exact trait I needed to implement for some behavior. So we have our largest function here, and let me turn off relative numbers. So we have this largest number, or largest function here from lines 13 to 23, and I'm taking in a list, and I don't know what it contains. I want to get the largest thing of the list, whatever that happens to be. Whatever that list holds may not actually know what largest is, which is why we need to have something that allows us to use this less than symbol. And that's fine, but if I don't know that that's standard compare partial ordering, then I'm kind of SOL, and I'll get an error here, right? Like binary operation cannot be applied to whatever the reference you're referencing inside of your list. If I actually do a cargo check, we get a more verbose error and something that I actually really like. This help section says restrict T, or whatever the generic is, to something that has to have standard compare partial ord. So if I didn't know that, it would just tell me, and I ended up using, I leveraged the help section of the compiler a lot as I wrote this. Maybe you, just like me, you're learning, wow, this is actually pretty useful and very helpful. So I really like the way that it kind of explains more stuff inside of the errors. Apart from that, there's not a whole lot here in terms of our generic examples that is worth delving too much into. One thing that wasn't particularly helpful and I didn't get an answer for was this idea of private attributes. The compiler calls them fields. I've been calling them attributes. I'm probably going to keep calling them attributes. So in this case, we have X and Y, and they are fields of our unconstrained point. That should mean that X and Y are private, and unless I do something like pub here, and also pub on the struct, I'm limited as to where I can access these private fields. So unconstrained point, even though it's private, is still accessible in this module. So if I go over here and we look down at main, we have an unconstrained point P1, P2. We also have this function mixup that returns a unconstrained point, as we can see from our Rust analyzer hint off to the side. What's interesting is I can call X and Y on P3, even though I don't own it. I do own P3 here, and I just thought this is why we write getters and setters. At least it is historically from the lens that I looked at it. So I tried to come up with some examples where this makes sense, and shout out to my friend Stu, who gave me some help and some thoughts as to how to make this. So I have 2 examples. Turns out that the usage of these fields is related to the module, not necessarily the actual object or struct. Here's case 1, and it was where I got the error I'm expecting to get. I make a struct and I make it inside of a module. So this module is called mod struct, and I made the struct called submod point. So when we want to access our point struct, we have to, wherever we're referencing it, call it from our mod struct module. We create our function here, and it's a reference to this. So ownership should be something we're concerned with in this case. So when I try to call px and py from outside of the module, even though the module and the struct are public, x and y are not public. So you'll see it says y and x are private fields. And if I go over here and try to run this, look at our verbose error, we see x and y are private fields. So we could fix this by doing getters and setters. What's funny is this feels very contrived. I needed to come up with a decent strategy for even getting this error. Most of the time that I'm imagining I'm using this, I don't really need to create getters and setters in the way that I was describing at the end of chapter 9. It's really nice compared to what I assumed, which was instead of these fields being associated with the struct, they're associated with the module and the ownership. I'm not sure if I'm using the right words in a lot of these examples. I want to make sure that I'm doing my best here. The long and the short of it is that the privateness of a field on a struct is in Rust associated with the module that owns that struct, and not with the definition of the struct itself or any modules that implement that struct, which is closer to what you see in a lot of other languages. Okay, the sentences are harder for me to say as we're moving through here, so hopefully that makes sense. I'm going to quickly uncomment my second case. We have our mod function. In this case, I'm making a module that contains a function that's going to be using data from a different place. I make sure I have my point available to me, and then inside of this point, right, this presumably needs to also be concerned with whether or not x and y are private. It's not in the same module. So when I import this and I make a function, in this case we're saying sub reference point, and when I call this one, it works perfectly fine. So where I'm calling this is down in this main function, and that's where point exists. So point and main, happy place, they're in their own module. Mod function isn't. I import mod function and subreference point. I create a point, and then I call it. Let me clean up these explicit types here. I have a point, and I end up calling subreference point, the thing that we imported, on a reference to our point. Subreference point does not own P. It's not even in the same module. And strangely, this one does work. I can still access X and I can still access Y. This feels weird because clearly we've established with case 1 that the ownership of a private attribute of a struct is associated to who owns it in a module perspective. And in case 2, we establish a different case for this, where the thing that is using the private struct attributes or private struct fields is not in the same module, and yet it can still access those private fields. I have one other point here that I want to try to express. I initially, when I was writing this out, was having a hard time with the Rust and not necessarily the concept that I was trying to express with the Rust. This was what I showed on the second example, and it makes sense because mod function doesn't have access to the point unless I bring it in. That is part of our super module or our base root module. So I need to actually bring that in order to use it for a parameter in sub-reference point. I didn't do that initially, and I got 2 errors. This one's obvious, right? Do exactly what you were doing. You actually import that point. When I was initially testing this, I saw the last error first. So let me show what that one says to me, and we'll see if you have a similar confusion that I do. So turns out English, we read from the top and then down. But for whatever reason, I was just looking at the errors from the closest to my cursor up. And this error E282 says we need type annotations. And so it said sub-reference point to our reference P cannot infer the type of T, which is part of P. So how do we actually define this? And I went through some silliness where I'm like, okay, let's be very explicit. I'll write out the types of these points and maybe the compiler can figure it out. And it was like, still, you don't have it right. And then it said, well, sub-reference point, when you're calling it, you might need to specify T and Y. And in that case, maybe it's good. And then it's still breaking, and it's like, well, what's wrong with T? I can't find it in the scope. And it's like, well, no, I'm telling you that it's a generic. And it turns out that the correct answer, the smart thing to do, is to read from the top down when you compile something and fix an error above. Because the way the signature is written for sub-reference point didn't make sense, the compiler then was not making sense with the way it was invoked. So fixing this with something I already knew, which was I need to import point in order for this to work, actually solved all the problems down here. It was able to understand exactly what I was referring to with T and Y. It's probably the first example I have where the compiler, it told me exactly what it needed to, but I had a problem with the way I was understanding the actual errors it was giving me. All right, jump cut back to the code we are expected to understand at this point. I have a couple other small little things to point out. One is that we talked about pow_i and square root as functions of floating point 32. I have the code off to the side. I might edit it to make it a little bit more visible. We have our actual pow_i for integer power and floating point power, and that depends on what we're actually passing in as a parameter to this method. Yeah, we can actually look that up pretty clearly, and at this point all of the definitions for our functions should make sense and lifetimes should make sense. So going through a lot of these, it's interesting because I wanted to see what's actually being called here. We have something called unsafe and intrinsics, but it's interesting to go to the source of the language and kind of have a better understanding of what's actually being written. I think that this is much more readable having gone through this chapter, and apart from some parts that let's just say we're unfamiliar with at this point, everything starts to make sense. So searching stuff in the documentation hopefully becomes a little bit more familiar to us as we move forward in these examples. That's about all I really wanted to say for our generic piece of this. Let's jump down to some examples from traits. I guess one thing that's useful to point out is that I wrote anything that I could with the nice syntax, where inside of the parameter space we can just place a colon and say this is the traits we expect to exist for this item, which is essentially doing the same thing as doing the trait bound syntax, where we explicitly define it as a generic. Yeah, I'm not gonna lie, I really like the other syntax better than the trait bound, so I'm probably not going to use a trait bound unless I need to. We had a couple examples where that was necessary later on, but we know it's a generic because we're not expressing a type explicitly. Similarly, we have another example with our trait bound and non-trait bound syntax. So for our first notify example, we have item, our generic, and we're saying it has to implement the following: summary and display. And we also have our trait bound example here. So for our notify function, we know that we're talking about one type. We call that out in our greater than less than bracket syntax. We say that type needs to have summary and display. And I like this because in my head right now, the ampersand and the traits kind of are fighting each other. And that's not even getting to the point where we have to concern ourselves with lifetimes in this. So when it gets particularly complicated, I'm probably just going to lean into the trait-bound syntax. I think that this is actually more readable when we're talking about multiple traits on one particular parameter. Multiple traits on one particular parameter, what would that look like if we used a where statement? I have a couple. So firstly, we have our grossiest, which is not using our trait-bound syntax. We have t, and then we have a reference that needs to implement two things, display and clone, and we have u, and u needs to be a reference that implements clone and debug. So we're talking about something that's already kind of long and maybe somewhat easier to read versus our trait-bound syntax, where we can actually just say some function has a generic t, and that needs display and clone, and it also has a generic u that needs clone and debug, and then our actual parameter space is just calling out what we're going to be calling those variables or types inside of our function, and then what they are, which is references to those generics. And our last one, which is where we get to use our wonderful where clause. So the actual signature here is just t and u as generics. Both of those are references inside of our parameters. And then when we actually concern ourselves with the traits that they need to inherit, or not inherit, but be restricted to, we can say where t and u and give them those traits with the little plus. I think this makes a lot of sense. I like this probably the most when it gets complicated. And just to be useful in terms of not just talking about the syntax of what would be our functions, but how they're actually called, I have the main call down here. There's not a whole lot that's super exciting. That's different than what we talked about in the book. I'll point out that we get compiler warnings pretty quickly if we're messing around with types that don't make sense. In this point example, we had one type we defined, and so since x and y are different types, we'll get an error, mix match types, expected a floating point number and found integer. I don't particularly like that error because it should just say x and y need to be of the same type. The error that the actual compiler run doesn't have any help syntax here. This would be very apparent if you just looked at the signature for point, but I think that something a little bit more clear in the errors of just like, this could also be an integer, also solves our problem. Yeah, I don't know. I'm not just picking at straws. I just wanted to point out that yes, I walked through that and looked at the errors. And if you're particularly interested in how notify and notify twice get invoked, we create our two structs for our tweet and our news article, and then we can pass them in and everything seems to just work. But that's not all we learned in this chapter. We also talked about lifetimes, so I'll go over the examples that I had, which is I make a largest call, and then this one would need lifetimes. If we don't include those lifetimes, it will throw an error saying you need a lifetime specifier. It's because none of our elision rules actually solved for this particular case. We have two inputs and one output. The output is a reference. We concern ourselves with the elision rules. So for our two inputs, we put a lifetime A and a lifetime B on both A and B respectively. And then we say, can we apply a lifetime to our output with elision rule 2? We can't. We have more than one output. And we're also not talking about a function. Okay, I can't make any assumptions. You need to fix that program or throw an error. In this case, as humans, we look at this and say, we cannot know whether or not A and B is going to be associated with our output T, because that's exactly what we're checking for on this line 11. And so we need to say that all of them are worth concerning ourselves with. So the lifetime of A and the lifetime of B are both worth considering for our output T. We have another example here. I just wanted to make sure I got an example with self. So I make a function largest, and that's going to be a method. So we are going to be looking at our third elision rule. Rule number 1, we have self, and we are going to apply a lifetime to it. We'll call it A. Rule number 2, we have one input, self, so we can apply the lifetime that exists for it to our output. So our output T gets our lifetime A. We also have our elision rule 3, which is, okay, are we using self? And we are, and we already have applied that to our output. I'm assuming that means that this gets skipped, but behaviorally it's going to remain exactly the same. We're comparing A and B, and we're returning either A or B. So we have to make sure we have our trait for partial ordering. And yeah, this all just makes sense and seems to work. I think it's fine. I had a question when I was writing this, which is like, what if I'm not actually using a reference to self, which is kind of silly, but let's write out that example. I turned off relative line numbers, but this is what this would look like if it was written out. And it's obviously a very silly method, but it does help us talk through our lifetimes and our elision rules. So largest but takes ownership is not a method because it's not a reference to self, but it takes ownership of self. So I guess it's a method. Kind of weird unless this is like a destructor, because what we're saying explicitly is at line 36, self is dead because it's no longer going to be in scope and we took ownership of it. And in this case, we're returning a reference to something T, and T is associated to what's going to be inside of self, right? So the compiler is actually able to pick that up, and it doesn't matter whether or not A or B is appropriate from a lifetime perspective, because we've failed at the point we're trying to return a reference to something that dies at the end of 36, right? There's the relationship to the inputs is no longer useful. There is no relationship once it dies on line 36. And it says as much. Error cannot return a reference to some local data, which is self, because it returns a reference to data owned by our current function. So obviously a contrived example, but gives us some level of reassurance that if we write something silly while we're not thinking and not caffeinated enough, that it's going to error in a way that leads us in the right direction. All right, well, that's all the interesting stuff that I had about this chapter. I think everything else was pretty well explained by the book and makes a lot more sense as you're just writing it out. So getting more familiar with Rust, always cool. If anybody has a good explanation for how those private fields actually work, or even better, if you're like, the book covers it, don't just keep reading, I'm okay with that too, but I'm still very confused as to how those end up working. I guess I'm just going to rely on the compiler to tell me when it is not appropriate, and instead of it being associated with the struct, it seems like it's sometimes associated with the module and ownership. I don't know. I'll also try to leave that code example somewhere. I'm not sure if the rest of this is particularly fun, but if you guys say that you want that, it's not a big deal for me to push it up. So thank you for watching. If you're watching this far, hopefully you learned something. I certainly have, and I will catch you in the next episode. If you have any questions or comments, please write them down. I try to read them all. All right, bye.